Thank you, Inigo. And let's go for the third speaker of this afternoon. Is Michael Geiselmann, co-founder and managing director of Ligentec, and his presentation is called Nonlinear Photonics Applications on a Silicon Nitride Platform.
Okay, thank you very much for inviting me here, and thank you for being here. I will talk about Ligentec. We are a company based in Lausanne, next to the Lake Geneva, 60 kilometers away from Mont Blanc, just across the lake. And we are offering low-loss integrated photonic circuits based off thick film LPCVD silicon nitride. This gives you very good losses and a very small footprint of your photonic integrated circuit. Technologies where we enable applications are listed here. Most of them we already have customers in a prototype phase, be it biosensing and microscopy, which is more in the visible, datacom, quantum computing, telecom, neuromorphic computing, LiDAR, which can be in both in different frequency ranges, augmented reality, and metrology. So if you're interested to discuss your application with us, I'm happy to talk with you afterwards. In this talk, I will I separate it in three stages. One, why would you use silicon nitride? We already heard this morning from Arne some advantages of silicon nitride. How can you access our silicon nitride platform? And I give you a few application examples. So most of you probably already have seen this graph, but still for those who are new to photonic integration, is you have here different platforms that have different transparency windows here in wavelength here. So silicon nitride is the only platform that you can access the visible range. Whereas indium phosphide and silicon nitride are all in the telecom range. This gives access to biophotonics or microscopy using silicon nitride, and you can also do sensing and datacom and telecom. Most of the differences of these platforms come with different building blocks, where each platform has a bit its plus and minuses. Where you have silicon nitride is very good in passive waveguides because of its very good losses and spot converters where you can directly attach single mode fibers. I won't go into detail into the others, but every platform has its plus and minuses, and what we try to do is to get the most out of our platform by heterogeneous integration with the other platforms, where our platform still lacks of functionality. So what questions that you should ask yourself once you figured out that silicon nitride might be the good platform to go to, is what thickness of the silicon nitride do you want to have fabricated? Do I want to go to PCVD or LPCVD silicon nitride? And what is actually the smallest geometry I need for that? And we made this plot, and this is similar to what Arne Leinse mentioned this morning. Is you can get very low losses by using very thin stripes of silicon nitride, but then you have these very large mode volumes and very big bends, that your cost of a potential chip is really high. However, if you go thicker in nitride or have other solutions like Lionics, you can still have reasonably good propagation losses, but now with a very small chip cost. So what Ligentec is guaranteeing is a loss of 0.1 dB per centimeter, and our chip size are usually 5 by 5 or 5 by 10 millimeters. So you can integrate a lot of components on such a chip. This is our main advantage and main unique selling point, is that we fabricate silicon nitride at 800 nanometer thickness with a loss better than 0.1 dB per centimeter, and can go down to a bending radius of 20 micron. So here you see a waveguide with the height of 800 nanometers, where the TM mode is fully confined in this 800 nanometer waveguide. And to the right here, a resonator that has a free spectral range of 1 terahertz. That means that your radius is extremely small, and you get extremely tight bending radiuses with very good confinement of your optical mode. And with this, we worked together with VLC and developed a process design kit, where one of the components is an AWG. That this is a chip, a 5 by 5 millimeter, where there's 4 different types of AWGs integrated, and a few other test components. So this is one of our test chips, and you get actually an area reduction of 300 times if you compare it to only a single stripe of thin film silicon nitride. Next question, what you need to understand is what is the difference between PCVD and LPCVD nitride. PCVD nitride is a low temperature process that can be integrated with CMOS, and the process dependent strain is not as much as in LPCVD. However, it has an absorption feature at 1500 nanometers, and if we want to go from there to stoichiometric, you have to deal with stress again. The other option is LPCVD nitride, which is a high temperature process. Here you can process stoichiometric silicon nitride, which is usually highly strained, and you have to deal with a strain for thicknesses above 300 nanometers, or you choose Ligentec, where we deal with the stress of at our 800 nanometer platforms. Due to the high temperature, you don't have any absorption features, and you get this very low losses. Options for integration in a CMOS line is then that you have to put the CMOS afterwards, after you deal with these high temperatures. Another question you have to ask yourself is how tiny are my smaller structures? What is the critical dimension of my smaller structure? E-beam lithography in principle gives you the smallest size, but there's a few points that you want to avoid, especially if you go to high volume. And this is why we chose to fabricate all of our devices on a deep UV stepper with this deep UV stepper lithography, where we have a critical dimension of around 150 nanometers. So you can fabricate it. You can fabricate structures or tapers that go down to 150 nanometers, still maintaining an 800 nanometer thickness. An additional advantage what the stepper lithography gives you is you have a very good overlay. So we also offer several depositions of silicon nitride to have 2 layers of nitride where you can pass your light from one layer into the other layer, and for that you need a very good overlay of the two layers. For production, it is very fast. It only needs seconds to expose a wafer, and you don't have any aliasing artifacts as you would have in E-beam fabrication. That is a bit the advantages of why silicon nitride is interesting. Let me now quickly go through how you can access the silicon nitride platform of Ligentec and the PDK we offer. We also offer these multi-project wafer runs where you use the design when you design, you use the process design kit we have developed and tested. However, the circuit IP stays with the customer. Then we fabricate this multi-project wafer run, do a test and measurement on quality control on the processing part, but also on the optical part on our calibration chips, and then you get a few 7 chips in our MPW will be delivered to you. And these are the 2 MPWs that we offer. We offer an MPW at 800 nanometers and an MPW at 150 nanometers, which is targeted for the visible wavelength application, and you can integrate heater modules or cladding opening modules that might serve you for bonding purposes or accessing the luminescent field for sensing purposes. And usually we have 3 to 4 MPW runs a year for each thickness. IR being the 800 nanometer thickness and visible being the 150 nanometer thickness. And we also offer dedicated runs where you can fine-tune your final silicon nitride thickness, especially if you're interested in dispersion engineering. This is something you could benefit from using a dedicated run. You can access any module we offer in our PDK, and you can have an expedite option to reduce the lead time to a few weeks, maximum 2 months of fabrication of a wafer. In our PDK, we have heaters and metal lines. We have inverse taper couplers, Mach-Zehnder, splitters, AWG, any passive component that we can directly integrate in silicon nitride. Further on, our process portfolio. So as I mentioned, we have this AN150 for visible wavelength and AN800 for infrared or 1550 nanometer wavelength, where in both the PDK is available and both are available in low-cost multi-project wafer runs. Additional to that, we have a multi-level photonic circuit where we can stack several stacks of silicon nitride. The local cladding opening, as I already mentioned, as well as the heaters, and an additional module that is at the moment only available in dedicated runs, a spot converter where you can directly match to a single mode fiber or to other photonic integrated circuits where we can tune the mode size of the outgoing or incoming spot. Let me quickly go into 2 things. One for the heaters and the local cladding opening. For the heaters, we take advantage of the fact that the mode is fully confined in the waveguide. So we can place a heater structure very close to the optical waveguide without interfering with the mode and introducing loss to the mode. And in this way, we can get a pi shift for at around 100 milliwatts, and we can even modulate with a Mach-10 interferometer the light at 25 kilohertz. We developed this local window opening in the beginning for a bonding purpose, but this window opening can also be used for sensing. So the only thing we do, we etch the oxide a way to get access to the evanescent field here, which is your silicon nitride waveguide. And we developed this process for the bonding. That means that our surface roughness is below hundreds of picometers over 10 micron range. And we have, in collaboration with UCSB, we have shown that we can bond here, for example, a lithium niobate structure that they use to generate the second harmonic generation of a CW laser. But also we have shown that you can integrate indium phosphide detectors, for example. And this brings me to application examples for thick film silicon nitride. We have discussed the benefits of this thick film, that you can have a very compact design, and the dispersion engineering is possible, which gives us access to nonlinear and quantum optics. And we have proven a high power operation up to 10 watt tested, probably even more. This one building block that I want to mention here is that you can get very long delay lines with very low losses below 0.1 dB per centimeter that only take, so this is a chip that is 5 by 10 millimeter that only take very few space on your photonic integrated circuit. So what is the nonlinear application of this silicon nitride? We can access the nonlinearity if we either put a lot of power or we use a very high Q cavity, which is given as we have a very good loss in our platform. We can build ring resonators that have quality factors between 1 and 10 million. In the latest runs, even we have seen quality factors up to 15 million. This is a resonance line width of between 10 and 100 megahertz. And so here you come with a CW pump. You couple it into this very high Q cavity, and due to the nonlinearity of the silicon nitride, you get 4-wave mixing out of this CW laser, and you can generate new lines. And here, due to the physics of it, this 4-wave mixing means that if you convert two photons from this frequency to one here and here, so these two photons are entangled. One thing that you need there is dispersion control, and this you get by changing the height and the width of your waveguide, so you are able to get to an anomalous dispersion regime in your waveguide. And this is just to show you how critical the height control is that we give to our customers. Here we have dispersion plots for TE and TM for 850 nanometer height, and compared to that, here dispersion plots for TE and TM for 750 nanometer height. So already a change of 100 nanometer in height gives you a change in the dispersion. And we are able to control this dispersion, and we have a height control by less than 1% of our LPCVD deposition. So one thing that you could do with this 4-wave mixing is you can generate not only 2, but you can generate a whole bunch of new laser frequencies, and then you call this a so-called frequency comp, where your laser lines are equally spaced. And this exists as a fiber solution, but mostly with spacings that are optically very hard to detect on an optical spectrum analyzer. If you go to an integrated circuit, you can make your cavity much smaller, so you can resolve your lines optically. And this is what we did in this CORES project together with NIST and UCSB and University of Virginia, is that they provided a tunable laser. Caltech provided a very high Q silica disk to generate the comp, and we provided a very high Q silicon nitride resonator integrated in an interposer chip. And so what this whole project is about is that they want to tune this laser here, but with the precision of 1 millihertz. So here we are at 200 terahertz, the optical frequency, and they want to step this laser by a precision of 1 hertz. And how they do that is that they use frequency metrology. So they have here a silicon nitride terahertz comp that they lock, so they can control the spacing of the comp and the offset frequency here. Lock this to a 15 gigahertz comp and lock this laser to that comp, and in this way you stabilize that laser to the precision that you can control the terahertz comp. And this is how a first prototype of this looks like, where you have here this big class resonator. Here you have our Ligentec interposer with the integrated high Q resonator, and here the laser that is directly butt coupled to that interposer chip, as well as this other resonator. And here the detectors are still missing to collect the signals. This is the sketch of the full device. Here our interposer chip has a bonding window opening where they bond 3,5 materials to do second harmonic generation, and here we have several in and outputs to put lasers and detectors. And here you see the tunable laser that is directly butt coupled to our chip, and they use here a red laser to align the two photonic integrated circuits. With this, we have shown that a total propagation loss was less than 4 dB going through 5 transitions, meaning from a fiber to a first layer of silicon nitride. Here we pass to a second layer of silicon nitride where we give access to an evanescent field, go to a splitter, and then back to the outcoupling. So we have achieved extreme low loss fiber coupling, as well as very high Q resonators in silicon nitride. And with this architecture, they managed to to tune this laser to dial it in to a certain frequency that they wanted, and this with the precision of a few millihertz. So if you compare just the zeros or the order of magnitude in frequency, if you compare the order of magnitude in dimensions, this would be moving a hair by the precision of a hair between the Earth and the Sun. This is what they did in the optical domain, moving the laser frequency that is 190 terahertz by 1 millihertz. Another application that we are working on is super continuum generation, again using a Chi3 nonlinearity in silicon nitride, and again you can dispersion engineer your waveguide by choosing the right width and height, and tune this dispersive wave emission that you get when your overall dispersion has a zero crossing, and like that you can with a very low power you can generate after 3 millimeters of propagation of a femtosecond pulsed laser, you generate a supercontinuum spectrum that goes from 600 nanometer up to 3.5 micrometers. Again, here precision of the width and height is very important, and at these wavelength ranges you need to have a material that is transparent for this wavelength in order to propagate it as glass is already absorbing. But as we have an 800 nanometer thickness, so there is still enough material to guide light at this wavelength range. So to sum up, Ligentec is a silicon nitride platform with a high mode confinement, a variable core thickness where we can adapt the LPCVD nitride thickness, and we have applications in visible telecom and mid-RR, and offer fast turnaround and MPW. With this, I would like to thank you, and I'm open for questions.
Thank you for the nice presentation. There is time now for any question. The audience? Any question? Well, I have a question myself about I would like to know a little bit more about the polarization dependence of the TIC waveguides. For example, which is the coupling between the fundamental T and TM modes in a band section?
So you can design the bends, so you can prefer one or the other polarization. So if for example, if you taper down, then you can prefer one. You can either kick out one polarization, or you prefer one over the other.
Okay. Thank you.
Well, in general, the technology platform is excellent and kind of looks very promising for broad wavelength range and nonlinearities and things like that. The wavelength range is a bit confusing. I think in the beginning on slide 5 you had this one slide that I've seen many other places as well. I don't know where it comes from, but it shows the kind of wavelength ranges in a totally wrong way. It's like a far infrared starting from 1600 nanometers, which is obviously not true and not in your following slide. So I don't know where this slide comes from, but
no, it should go up. It should go up to even to 8 micron. The silicon nitride. You referred to the silicon nitride or to the silicon?
Yeah, basically to this picture. I was wondering where this comes from, because this far infrared normally starts from somewhere like a tens of micrometers and not like 1.6 micron.
Okay, I will take this comment and update that.
Yeah, but otherwise the platform, that was like a comment on this particular one. I don't know where it's not done by you. I've seen it many other places as well. So what about the fiber coupling? Maybe. So how good is that to a standard single mode fiber? I believe you can make very good coupling to.
Yeah, Yeah, we have a new way to couple single mode fibers to our platform, where we get losses of around 1 dB per facet. Afterwards, it depends of the packager. You can even go down to 2.5 dB per facet to couple a SMF28 fiber.
Looks very good.
Any other question? Okay, right there.
What is the edge uniformity that you have across your wafer? I didn't see the size of the wafer that you produce.
So
yes.
For prototyping, we use 4-inch wafers. From a certain volume production on, we can also go to 6 and 8-inch wafers. But what was your...
The edge uniformity of the silicon nitride, especially if you have the 800 nanometer, how well you can control across your wafer?
So it's a deposition.
I mean the edge of the waveguides.
You mean the height of the waveguides? The height of the waveguides are controlled by less than 1% over wafer.
Okay, any other question? If there are no more, let's thank the speaker again.